Can you find all the meteorite Eulers in Papa Flemmy's random week? Maybe. If you did, please comment. Good morning, fellow mathematicians. Welcome back to another video. Once again, it's time for
Papa Flemmy's random week.
Oh yeah, let's go ahead and get started. As you might notice, on the chalkboard right here, there's a famous boy. That's Papa Schrödinger, the stationary Schrödinger equation. And we want to solve it today for a given potential. This potential being, if you take a look into the description, there will be a link to some potential, v of x being equal to k over 2 times x squared. And this right here is exactly the potential for the harmonic oscillator, the classical harmonic oscillator. And if we plug this into this quantum mechanical system right here, we end up with the quantum mechanical harmonic oscillator if we solve for those little psi's right here, the wave functions. Also, we can equivalently rewrite this as 1/2 m times omega squared x squared. And we can plug this potential into here and see what we get. So, we want to derive the quantum mechanical harmonic oscillator today. So, doesn't that sound exciting? The word sounds quite complicated, so it must be exciting. So, E times psi is nothing but minus, and Papa Planck, we are just going to call it h for simplification purposes, squared over 2m del x squared of psi plus. And this is 1/2 m omega squared x squared times psi. And we want to lay some groundwork. We want to do some basic factoring out and stuff like this for a nice foundation of solving this right here. So at first I would like to advance this fraction by m over m, so that we end up with m squared over 2m in that case. So we can do that, that's equivalent. And also we could factor out this 1 over 2m squared on both terms and also this psi. Don't forget to bring the psi to the right hand side, because we have this differential operator right here. Don't bring it to the left hand side, that would be not equivalent. So we end up with 1 over 2m and then times minus h squared del x squared plus m squared, no, let's factor out the squared on all those terms, m times omega x, but the whole thing squared, times psi. Okay, great, so that's a nice foundation. And I want to introduce a new something, it's called the momentum operator. It's denoted by p, so just like the classical momentum, you can also place a little roof up here. We are going to leave it without a roof for simplification purposes. And it's defined as follows, it's negative I times h del x. So that's the momentum operator. And if we square that thing, what are we going to end up with? P squared is nothing but, so minus 1 times minus 1 is just positive, I times I is going to be negative 1, and then h squared del x squared. And great, you see, this right here is exactly this, so that's the momentum operator squared. So let's plug this in. 1 over 2m, then the momentum operator squared plus m omega x whole thing squared times psi. And another little notation, this thing right here is called the Hamiltonian. That's also an operator. You can also place a little roof up here, you don't need to. And our goal is it now to factor this Hamiltonian right here. So that's our goal for now. And I want to make a little remark at this point so that you see where this comes from. This factorization. So if you take 1 over a and then u squared plus v squared. This is the difference of two squares if you take a closer look, because if you take I squared right here and then a negative sign, we are ending up with the difference of two squares. And also we can turn this right here into 1 over square root of a, but the whole thing squared. And now we can turn this around a little bit, so we can factor stuff out, we can expand it a little bit into 1 over square root of a, and then u squared, u plus I times v, and then 1 over square root of a, u minus I times v. So that's basically the idea behind factoring this Hamiltonian right here. And after factoring, we are going to get something that's called the ladder operators. we are going to solve this equation right here algebraically today. It's my most favorite way of solving a differential equation ever. And we are going to introduce those ladder operators as follows. They are called a plus or minus, and they are going to be defined as 1 over square root 2 times m times h times omega, and then times negative, positive, I times p, and then plus m times omega times x. So that's nearly what we wanted. So if you take a closer look, if you factor it that way, the only thing that's different is this 1 over h times omega. It has a purpose. Some smart people thought about how to factor this in a nice way. And now we are going to play around with those ladder operators in the next few steps. Let us move on, ma meteorite Euler boys. Maybe there's a meteorite Euler flying through this video right here, right now. Can you find all the meteorite Eulers in Papa Flemmy's random week? Maybe. If you did, please comment. Let us move on. So just like I said before, we want to play around with a plus and a minus a little bit. But at first, a little remark. If we end up with, for example, p times x, this expression right here is not abelian. That means it's not equal to x times p. If you write p out, you end up with a differential operator. So that means here you would differentiate x with respect to x, and right here you wouldn't differentiate anything. So this isn't equal. That little fact is really important. So at first, why not multiply, for example, a plus and a minus together, or a minus and a plus? So let's go ahead and get started. A minus times a plus. What is this going to be? Well, we have this factor squared right now. So 1 over 2 times h times m times omega. And now, a minus times a plus. A minus corresponds to the positive sign right here. Positive I times p plus m times omega times x. And then times. The positive branch right here corresponds to the negative I times p. So negative I times p times m omega x. And now, as always, we can factor stuff out. So let's do it step by step. What do we end up with? At first we are going to have I times p times minus I times p. Minus and positive is going to be minus, but I squared is negative 1, so we end up with a positive sign, and p squared. So the first step is going to be p squared. And now we have this times this, so plus m omega x, but the whole thing squared. And here's the important part. Now we are going to multiply I times p times this chunk right here. So plus I times p m times omega times x, and also we are going to multiply m times omega times x with this right here. So we end up with minus m omega x I times p. And just like I said before, the order is important this time, so you can't just multiply this term with this and change it around. So we need to leave it as it is right here. Okay, great. Let's bring it into in a proper form, factoring stuff out. So we end up with 1 over 2 times h times m times omega, p squared plus m omega x, whole thing squared. And now I want to factor out minus m times omega times I, for example, minus I m omega, and in parentheses we're ending up with, we have to change around the signs, xp minus p times x. Remember this fact, it's really important. That's something my fellow students don't get right away. Those are not abelian, so that means they are not cancelling out. And I want to introduce some new vocabulary to you guys. That's something that's called a commutator. And it just gives you an idea how badly two terms commute. And the commutator is defined as follows. So if we have a and b, that's notation for the commutator. It's nothing but a times b minus b times a. And if you look at here, that's the commutator of the distance and the momentum. And we would like to find out the value of this thing right here. But it's not as straightforward as you might think, because we have this differential right here. But this term right here doesn't really tell us what we are going to differentiate. So why not multiply the commutator x and p by some function f of x and see what we get. So we're going to end up with x times p f of x minus p times x f of x. And don't forget what our p was. Our p is nothing but minus I times h del x. Okay, keep this in mind. So now we can plug all the information in. We end up with x and then minus I times h in this case del x f of x and then minus. So now we have minus and minus are going to become positive because we have this minus sign here. So positive I times h and now del x of x times f of x. And as you might notice, we have to use the product rule on this one right here. So let's expand everything. So this first term stays as it is. Minus I times h, x, del x, f of x. And also plus I times h. The first part, we are going to leave f of x as it is, and we are going to differentiate x with respect to x. It's just 1. So f of x in that case. Next term, we are leaving x as it is, and we are going to differentiate f of x with respect to x. So positive x times del x f of x. Great. And if you take a closer look, this and that term are the same, but with a negative sign. So this and that is going to cancel out, and we are ending up with I times h f of x. And now we would like to compare coefficients in that case, and you might notice the commutator times f of x is equal to I times h times f of x. So we can conclude that the value of this commutator right here is nothing but I times h. You can do the same procedure with the commutator of p and x. You are going to end up with minus I times h, but we don't need this fact right here. Great, we can plug this information into here. So we don't need this anymore. Now we have 1 over 2 times h m omega. We have p squared plus m omega x whole thing squared. And now minus I times m omega and then I times h. I and I are going to become positive 1 and this negative sign right here. So negative 1 times negative is positive. And now we came pretty far on that already. Yeah. Let's play around with this expression on the next chalkboard. I don't have much space left. I'm back. Let's solve this even more every day. I hope you got this reference. What we can do now, we can bring this factor right here to the inside a little bit. And you might notice that m times h times omega is going to cancel out with this factor, and we are going to end up with a 1/2. So let's conclude this at first. So we end up with this factor, 1 over 2 times h times m times omega, p squared plus m times h, m omega x, but the whole thing squared plus 1/2. And if you take a closer look, or you can play back in the video, you might notice that this right here is exactly the Hamiltonian times a factor of 1 over h times omega. Let's conclude this. So a minus, a plus is nothing but 1 over Papa blank omega, the Hamiltonian, plus 1/2. And that was the point of creating those factors right here. We wanted to put them together to get an expression for our Hamiltonian right here. So that's nice. Okay, but why not isolate this Hamiltonian right here to get a final expression for it? So we can subtract 1/2 on both sides, and we can multiply both sides by Papa blank times omega, not equal to 0. So we end up with Hamiltonian being h times omega, a minus, a plus, minus 1/2. You can do the same spiel for a plus times a minus. All that's really different is that we are going to end up with a different sign right here. This stems from the fact that we can turn around the order of this commutator and we end up with a negative sign on those I times h. So that also means that the Hamiltonian is also h times omega, a plus, a minus, plus 1/2. And we can turn this into one big expression for the Hamiltonian. We now know that the Hamiltonian is nothing but h times omega, a minus plus, a plus, minus minus plus 1/2. This might look scary, but it's nothing but this right here. A little generalization. Whew, so that's great. Can we do anything else with this product of this ladder operators? Let's see if those two do commute. So why not add the equations of those together? So a minus, a plus. And then, for example, adding a plus, a minus, or subtracting it. It doesn't quite matter. No, let's subtract them. Okay, what do we end up with? This is going to be 1 over h times omega, and then plus 1/2 in this case. And now subtracting this formula right here, we also have the Hamiltonian. Subtracting this is negative 1 h times omega times the Hamiltonian minus 1/2 in this case. No, minus and minus is going to become positive. Don't forget that. This and that is going to cancel out, and we end up with a 1 right here. That's interesting because you see this right here is exactly the form for the commutators, and if you turn them around you are going to end up with a negative 1, probably. Try it out for yourself. So that also means that there's a commutator of this term first and then this term, a minus, a plus, and the value is just 1. Maybe this does help somehow. Don't forget, in the beginning I said that we wanted to find out the wave function that solves the Schrödinger equation for the given potential. So why not plug our value for the Hamiltonian into our Schrödinger equation and see if this helps in the least bit. So don't forget, the total energy times the wave function is nothing but the Hamiltonian times the wave function. Plugging in the Hamiltonian leaves us with Papa blank times omega, a minus plus, a plus minus, minus plus 1/2, and then times psi. And now we have a little problem. How in the hell are we supposed to find out this psi right here, this wave function? I mean, we have found an expression for the Hamiltonian, but it's still just an eigenvalue problem. So how are we going to proceed? Sometimes physicists try to construct certain wave functions, for example, that maybe solve equations like this. It's like an ansatz, you could say. So why not construct new wave functions that may be able to solve the Schrödinger equation with certain energy levels? So let's try this out. So why not make an attempt on combining this wave function right here, or a different function in that case, with one of those ladder operators right here. And by doing this, you might see why those are called ladder operators in the first place. So why not let some new wave function be a plus times psi? And all that we really want is to plug this wave function into our Schrödinger equation. That means combining this Hamilton operator with this wave function and see if it solves our Schrödinger equation with a certain energy level times this given wave function. So let's go ahead and get started. So h times a plus psi is now. And it doesn't matter what branch you take of this Hamiltonian. For simplification purposes, which come apparent in a second, we are going to choose the positive branch of this thing right here. So h times omega, a plus, a minus, plus 1/2, and then our wave function, a plus times psi. We can bring this a plus to the inside, for example. So we end up with h times omega, now a plus, a minus, a plus, and then plus 1/2 times a plus times psi. And don't forget, those are not commuting. This doesn't work. But we could factor it out maybe, for example, this first term right here to the left side. Can we do this? Well, we could do this if we could change the order of 1/2 and a plus. And we can, because 1/2 isn't exactly an operator right here. So that means we can interchange those. This is just a constant, a scalar. So let's bring this a plus to the front and the 1/2 to the behind. And now we can factor out a plus on this. That also means we end up with h omega, A plus times A minus A plus plus 1/2 times psi. And for the same reasoning, h times omega is just a constant, so we can bring this A plus to the front. So those are basic steps you need to explain when working with operators and stuff like this. Now something handy comes in. We have this relationship right here. What is A minus times A plus? So don't forget, I'm putting it here once again. We have this relation. A minus, A plus, minus, A plus, A minus is equal to 1. So A minus, A plus is now nothing but A minus, A plus is nothing but 1 plus A plus, A minus, or A plus, A minus plus 1. So we can plug this new information in. So this is A plus H omega. And now this right here. A plus, A minus, plus 1/2, and then plus 1. I'm putting it this way. Okay. And now we can bring this H times omega to the inside, for example. So we end up with A plus times H omega, A plus, A minus, plus 1/2. Maybe you can already see why I put it that way, plus H times omega times psi. And this right here is exactly our Hamiltonian once again. This right here is the Hamiltonian. And now we can bring this psi to the inside, for example, and you might notice that the Hamiltonian times the psi is nothing but the energy of the system. So the Hamiltonian is the value for the energy. So we can also rewrite this Hamiltonian as the energy. So that's equivalent. And also we can bring this A plus to the front because our energy is constant in the end. So we end up with E plus H times omega, A plus times psi. I hope you see where this came from. So we have this initial, we have this eigenvalue problem up here, and our Hamiltonian is corresponding to this energy right here. So our Hamiltonian can be set equal with the energy, and it's constant, so we can bring this A plus to the front, and so on. That means we have solved the Schrödinger equation using this wave function with this energy. But what does that actually mean? So we started off with a certain energy level, and we have raised the energy level by h times omega, which in itself is just an energy. That means if we apply this operator right here, this A plus, we are going to call it raising operator, then that means we are going to raise the energy by a level of h times omega. You can go through the same procedure with A minus times psi, and you are going to end up with a value of E minus h times omega, A minus times psi. This is the lowering operator. So that means we are decreasing the energy level by h times omega every time we are using this operator right here on a wave function, on the Schrödinger equation. And that is kind of brilliant, to be honest, because we can make use of that to solve for some wave function right here. Can you see why? Well, we can have certain energy levels, and by this definition right here, our energy levels are going to be discrete. We are going to increase it by some natural numbers times h times omega. That's nice. But if we apply this thing right here repeatedly, this lowering operator, that means we eventually are going to end up with a negative energy level. So lowering the energy again and again and again, we might end up with a negative energy, for example, and that doesn't exactly work. So maybe there's some kind of ground state, so some lowest energy level. And we are going to solve for it now. So what does this reasoning actually imply? So that means we are going to use this lowering operator again and again until we reach the wave function for the lowest state, for the ground state. And if we use it on that ground state, we are going to end up with an energy level of 0. So what does that mean in mathematical form? a minus times some psi naught, we are going to call it psi naught for the lowest state possible, is going to be 0. And that's the homogeneous differential equation. First order, and that's nice, we can actually solve that. That's really easy. So when I plug the information for a minus in, what was a minus? It was 1 over square root 2 times h m omega times. And then we ended up with a positive I times p and also plus m omega x and then our psi naught. I'm doing this all out of my mind. That's why it takes a few seconds to compute in my head. That's just a constant, we can cancel it out. We don't want to cancel this out, we don't want a trivial solution. So right now we are going to end up with 0 is nothing but I times p plus m omega x times psi. And don't forget what our p actually is. Our p was nothing but minus I h del x. We can plug this in. I and I is going to become -1, but we have this negative sign, so this is going to be positive. So we have h del x times this psi right here. So that's the derivative of this psi naught in this case. Don't forget your knots. And also plus m omega x psi naught. We can bring stuff to the other side. For example, subtracting this on both sides. That's going to be a negative m omega x psi naught is now equal to h del x psi naught. We can divide both sides by Planck's constant right here, not equal to 0. And let's divide both sides by this ground state wave function. Not equal to 0, that's our condition, so we don't want to get the trivial solution. Let's divide it. And this is in terms of x with respect to x. And now we are going to integrate both sides with respect to x, actually. So that's how we are going to solve this. I made a series on that. This right here, you can introduce some substitution, it doesn't quite matter. This is going to end up with del n of psi naught. And integrating this right here is quite easy. That's a constant, we can bring it to the outside. Integrating this, raising it by a factor of 1, this power right here, and dividing by it 2, we end up with minus m omega times 2 h x squared. All that's really left to do is exponentiation, but don't forget you have a constant right here, a constant c, because we had an indefinite integral. Now we end up with psi naught being nothing but e to the minus m omega over 2 h x squared plus some arbitrary constant c, but we can use the rules of exponentiation to break this up into this term times some other constant, e snack, e Schlange. Let's put it that way. Okay, great. And now we would like to solve for this thing right here. So we would like to find out our constant. How are we going to find it out exactly? Well, we could normalize this wave function right here because wave functions need to be normalizable when dealing with the Schrödinger equation. So that also means that we want to take the improper integral from minus infinity to infinity of this square right here, absolute value of the square, dx. So we want this to be square integrable. We end up with. So this is going to be a constant still. And we want this whole thing to be 1, so that's the condition for being normalizable. Let's put it here. So we can bring this to the outside. Absolute value is snack squared, indefinite integral right here. And also we have this thing squared now, so that means the 2's are going to cancel out. E to the minus m omega over h x squared dx. So I hope you can see where this came from. In the normal case, you need to take the complex conjugate times the wave function itself, but our wave function is real. That's why we don't have a complex conjugate to be exact. So we are just going to square this thing right here, getting rid of the 2. I hope you could follow this. And integrating this is really quite easy. I've made several videos on that. We are going to end up with absolute value of e snack squared. And now this is going to be square root of h m omega, and also a pi up here. Yeah, right. That's basically it. And now we can actually solve for our normalization constant right here. So dividing both sides by this stuff right here and taking the square root. And also we need to choose the positive branch after taking the square root, because we have the absolute value of this thing right here. That also means that our E snack is now nothing but taking the reciprocal of this thing, m omega over pi times h, and also square root is to the 1/2 power, and then also taking the 1/2 power once again is to the 1/4. And that's absolutely nice. We've got something to work with. We have our first initial wave function, the ground state. And our wave function is now psi naught with respect to x, will be nothing but, what do we have? It was constructed like this right here. So we have this factor m omega over pi times h to the 1/4 power e to the minus, and m h over 2 omega, no, I mixed it up, omega over h x squared, and that's it. So we have found our ground state, and this thing solves the Schrödinger equation with a certain energy. But what is that energy level? Well, we can just plug this thing into our Schrödinger equation and see what we get. Don't forget what our original Schrödinger equation was. Energy times the wave function is nothing but the Hamiltonian times the wave function. And we want to find our ground state energy. So that means our energy level at the point 0 in this case is just the Hamiltonian times this psi 0, psi naught. So this is our equation right now. So why not solve this right here? And we can choose one of those two Hamiltonians. It's easier to choose the positive branch once again. So h omega, and then we have a plus, a minus, plus 1/2, and then also times psi naught. That's supposed to be a 2 down here. And the good thing is we can bring this psi naught to the inside, actually. So that means we end up with h omega, a plus, a minus, plus psi naught, and then plus 1/2 psi naught. And don't forget what our initial condition was for this psi naught right here. It was for our ground state. A minus times psi naught is 0, so that was our boundary condition for this. So this is going to be 0, and we end up with 1/2 h times omega times psi naught. And this right here is our ground state energy. So we can compare the coefficients, our eigenvalues, and we know that our ground energy is nothing but h times omega over 2. And that's nice. And just like I said before, or just like we proved before, we can now apply the raising operator to this ground state repeatedly, one after another, to get new and new, more and more energy states. And every time we are doing this, we are going to raise the energy level by h times omega. So what would be our nth energy level? So we are taking this ground state right here and adding h times omega all the time. That means we end up with 1/2 plus n h times omega. So that would be the nth energy state. I hope you can see where this came from. And also our n is element of the natural numbers, including 0. Yeah, nice. And what would be our nth wave function? So that's the main question here. We wanted to find out our nth wave function. Well, our nth wave function is constructed as follows. Psi n with respect to x is nothing but, well, we have some normalization constant that is going to pop up. Just going to call it an, so the normalization constant of the nth state. And we are going to apply this a plus repeatedly, n times, to the ground state with respect to x. Et voila. This right here is exactly the solution to our quantum mechanical harmonic oscillator. That was quite a trip. And this video is taking forever. That's why I'm not going to derive this an in this video. That's left as a little exercise for the reader. No, just joking. I'm going to make a little bonus video on that at some point of time. I hope you did enjoy this little excursus into quantum mechanics. I hope this video was okay. Videos like this are quite hard to make for me because they are long as fuck, and also, well, it's a lot of vocabulary I have to remember and stuff like this. I mean, it comes naturally most of the time, but I'm remembering all the stuff, so I have no real preparation for those videos. I just know what to do, and then I'm going through it while making the video. So I hope you did enjoy this. If you did, please like and subscribe and recommend me if you like. If you want to support me a little bit more, link to my Patreon is in the description. I would appreciate support from you guys highly. Up until the next video, have a quantum mechanical day, my boys. See ya.
Das dritte.